Good evening, everyone. Sorry if I scared you while you were in any fun conversations. Welcome to the public lecture hosted by KIPAC, the Kathleen Institute for Particle Astrophysics and Cosmology. My name is Sinan Du, and I am the Outreach Engagement Manager at KIPAC. I will also be your main host tonight. So it's wonderful to see many of you here in person. And we also have an online group of comparable size who is watching the live stream. As some of you may already know, we try to feature lectures on topics that you are really interested in hearing about, or topics that are timely and also relevant. So tonight's lecture was selected based on this ladder criteria. You may or may not have heard of the heliophysics big year, which started about a year ago. So this is a global celebration of the sun's influence on Earth and also on the entire solar system. We started the celebration with a solar-related public lecture last October, and we're also going to wrap up the celebration with tonight's talk also talking about the sun. So if you're here to learn more about aurorae, the recent heightened solar activity, or just in general wondering what the sun is doing, you're at the right place. So before we start, I would like to give a big shout out to the entire team who is supporting this event behind the scenes. So you may have already met the front desk staff. We also have our tech team here, and Leon is also helping me manage the live stream. And we also have the online chat moderators who are subject matter experts on this topic, and they will be managing answering questions online. So I'll just give them a quick second to introduce themselves so everybody can know them. First, we have Boyang.
Hi, I'm Boyang. I'm a student in the Stanford Solar Physics group. It's my pleasure to be helping with the chat today.
Great. Thank you very much, Boyan. Next, we have Sushant. And for those of you who may remember the last solar lecture last year on the day of Halloween that was given by Sushant.
Hello, I'm Sushant Mahajan. I'm a postdoctoral fellow in the solar physics group at Stanford.
Great. And last but not least, we have Shay.
Hey y'all, I'm Shay Hessweber. I am an early career research scientist in the Stanford Solar Physics Group, and I'm very excited to be answering your questions today. And hi, Oana.
All right, well, thank you all. For those of you joining online, you'll see the live chat box on the right-hand side of the YouTube page where you're welcome to enter all the questions you want to ask and also engage in discussions. So most of the questions will be answered by the chat moderators, and the remaining field will be saved for Oana to answer during the Q&A. And for all of you joining us in person today, you have the chance to directly ask your questions during the Q&A. And of course, you are encouraged to also chat with Oana one-on-one after the talk. So now it's my great pleasure to introduce tonight's speaker, Dr. Oana Vesa. Oana is a postdoc researcher here at Stanford in the solar group. Her current research focuses on using waves to probe the interior of the sun and also investigating how these waves are connected with solar dynamo, which is the process generates and maintains the sun's magnetic field. Oana got her bachelor's from Albion College in Michigan, after which she got her PhD in astronomy from New Mexico State before joining Stanford as a postdoc. So Oana is a first-generation college graduate, and that makes her extremely passionate about science communication and hoping to share her love for solar physics and also inspire everyone's interest in science. So without further ado, let's welcome Oana.
Okay. Hi, everyone. Okay, so Imagine the sun as a gigantic engine fueled by its magnetic field. This powerful force drives everything we see happening on the sun, from sunspots to solar storms. And these solar storms aren't just interesting to watch, they actually reach far out into space and impact Earth directly. Now, over the past several months, this engine has been revving up, and the sun has become more active and dynamic, showing us an increase in sunspots and solar storms, as well as producing the lovely auroras we've been seeing lately. So let's explore what's been going on the sun. So our closest star, the sun, has definitely made splashes in the news recently, with the recent solar eclipses that reached millions of people on the continental US and brought communities together, to the solar cycle ramping up and creating these brilliant auroras lighting up the night skies as far south as Hawaii, a first in over a century. In general, some of these events were actually a first for many and a wonderful way to learn more about our sun and experience its temperamental nature. However, while the sun's recent burst of activity has produced wonderful auroras, high solar activity can have a range of impact on Earth's technology, infrastructure, and even human safety. Powerful storms on the sun can directly impact power grids, GPS, satellite systems, electrical grids. Notably, in 1989, a powerful solar storm reached Earth and knocked out power lines in Quebec, Canada, causing a 9-hour blackout that affected millions of people. And this event pushed energy providers to improve safeguards, yet even today, high solar activity remains a challenge. Recent storms have caused irregularities in our power grids and disruptions to GPS-based systems. So much so that in May of this year, during a very, very severe sequence of solar storms, farmers using GPS-driven John Deere tractors were actually unable to use their tractors during peak farming season. There were even reports of Google Maps not working properly. Satellites were also affected as well during these May storms. Some NASA satellites lost data, and other satellites in low Earth orbit were actually being dragged back down towards Earth at a rate of nearly 600 feet per day. And this sort of triggered a lot of chaos as thousands of these satellites had to quickly maneuver to maintain their altitude. And this could have been very catastrophic. So space weather even poses events for humans. Oh, sorry. So space weather even poses risks for humans such as astronauts oh, there we go. Okay, as increased solar activity causes radiation exposure even in space. And during past storms, some airplane flights actually had to be rerouted as safety precautions. So and all of this sort of highlights how dependent and intertwined our technology is with the sun's dynamic activity. A powerful solar storm today could cause widespread damage, impacting things like power grids, GPS systems, our communication lines, and this could cause trillions of dollars worth of damage. But to better understand space weather, we have to look at the literal star of the show, the sun. So the sun is a big ball of hot gas called plasma. The interior or the inside of the sun can be divided into these 3 distinct regions. You have the innermost part, which is the core. This is this creates 99% of the sun's energy. And the energy generated in the core then travels up towards the surface of the sun. As the energy travels towards the next layer, which is the radiative zone, here energy is transported via radiation, and it can take light nearly a million years to make it through this region. Then we have the outermost part of the solar interior called the convective zone. So the convective zone is outermost part of the interior of the sun, and energy travels here through convection. And so here we actually have hot blobs of plasma are formed and they're buoyed up towards the surface. And this process is actually similar to boiling water. So if you have water, so as the water boils, hot bubbles rise to the surface, they'll pop, and then they'll fall back down. And this process continues as long as there's water left to boil. And in the sun, a similar process happens. You have these hot blobs of gas, some as big as Texas, that rise up to the surface. They reach the surface, cool, and then sink back down again. And so this is called granulation. So here's an image of, there's an image of it over here. And the colors are actually related to the temperatures too. So the hotter part of this granule is this lighter color. So that's the part that I'll see that goes up to the surface. And then this darker part is called the intergranular lanes. And here is where you have this downflow of hot gas. And this process just continues and continues. The sun also has these three distinct atmospheric layers. So you have the photosphere, which is the visible surface of the sun. And this is what the sun would look like if you looked at it just as is, but please don't look at the sun directly. And the photosphere of the sun is marked by those granules. Then we have the middle layer of the middle atmospheric layer of the sun, and this is called the chromosphere. And it's characterized by this red hue, and you can typically see it during solar eclipses or with special satellites or special telescopes and satellites. And then lastly, we have the outermost layer of the sun called the corona. This is characterized by this halo, like crown-like effect. And the corona is what you see during a solar eclipse. One of the biggest problems in the field at the moment is called the coronal heating problem. So one would think that all the energy is generated in the core of the sun, and it's extremely hot there. And as the energy travels to the surface, things will sort of cool down. And then this does happen. The surface of the sun is relatively cool. However, all of a sudden, it experiences a steep increase in temperature. And in fact, the corona can reach millions of degrees Fahrenheit. And we don't really understand why. So while this big ball of hot gas is more than 90 million miles away from Earth, its impact on Earth and our environment is massive. We essentially live in the atmosphere of the sun. Every day, a powerful stream of charged particles called the solar wind bombards us from the sun's outer atmospheres over 1 million miles per hour. And these particles constantly hit Earth's magnetosphere or its magnetic field. And the magnetosphere acts as a protective shield. So this animation up here shows what the solar wind looks like in space captured with NASA stereo satellite. So you can see it's sort of like an extreme sandstorm. Normally, Earth's magnetosphere protects us from a lot of the harmful effects of the solar wind. However, sometimes when the solar wind is really powerful, that can leak through and interact with our atmosphere. And this interaction ends up producing these beautiful auroras. So the charged particles from the solar wind interact with gases in our atmosphere, namely oxygen and nitrogen. And when they do this, these gases release light. And so oxygen gives you the sort of red color that you see here, and nitrogen will give you this sort of green color. The sun can also release giant storms. We're talking about huge bursts of plasma, magnetic fields, energy, material from its outer layers. And when solar activity increases, these events are much more frequent. So some solar storms include things such as coronal mass ejections and solar flares, which I will discuss in upcoming slides. So this animation shows what happens when a powerful storm called a coronal mass ejection heads towards Earth. And when this happens, it can trigger strong geomagnetic storms or disturbances in Earth's magnetic field. And these storms are what causes the space weather effects I mentioned at the beginning. So these storms can they can not only cause auroras, but they can also cause disruptions to our power grids, our GPS systems, and essentially our infrastructure. Now let's dive into what these solar storms or eruptions actually are, using images and animations from recent events that have happened. So a solar flare is a sudden, intense burst of energy and light from the sun, and it occurs when the sun's magnetic field twists and strains under pressure. So think of magnetic fields as giant rubber bands. You have a giant rubber band, you pull it, so you stretch it and you twist it. Well, at one point you have two choices here. You can either let it go or you can keep pulling it and it'll snap. Well, let's say you just let it go. It will snap back like this, and that on the sun is what releases this massive explosion of energy. And that's what's called the solar flare. And this release is extremely powerful. We're talking about 1 million times stronger than a volcanic eruption, 1 billion megatons of TNT. It's an insane amount of power. And solar flares send out high energy radiation, such as X-rays. And all of these reach the Earth in about 8 minutes, which is how long it takes sunlight to reach Earth. And these events can last several minutes to hours. And like earthquakes, solar flares vary in strength and size, with the strongest actually being called an X-class flare. So these are two images of X-class flares, and you can see Earth here to scale. It's really tiny, comparison everything. And sometimes the same area on the sun that produced a solar flare can actually produce multiple solar flares in a row. On the other hand, coronal mass ejections, or CMEs, are huge eruptions of plasma and magnetic fields. So they release vast amounts of hot electrically charged gas and magnetic fields into space. And these massive clouds, you can see here's one, and then over there, oops, sorry. Well, over there in the animation. So these huge clouds of gas can release billions of tons of material at speeds of up to 1 million miles per hour. We're talking extremely fast. And sometimes they can reach Earth in as little as 15 minutes, although it can take several days. And when directed towards Earth, the CMEs can create these intense geomagnetic storms, or again, disturbances in Earth's atmosphere that cause space weather events. And CMEs occur similarly to solar flares, yet they don't necessarily occur together. They can, though. And strong coronal mass ejections are actually the reason why we've been able to see auroras this far south. So typically, auroras are limited to the polar regions of Earth. However, strong coronal mass ejections can boost auroras, making them visible much farther south than usual. And again, this is why we've been seeing these auroras as far south as California. This was taken in, well, the image at the bottom over there was taken at Joshua Tree. But why have we been seeing so many solar storms recently? To answer this, we actually have to talk about sunspots and the solar cycle. So sunspots are regions of dark patches on the sun's surface that are cooler than the surrounding. Sorry, okay. So sunspots are dark patches on the sun's surface that are much cooler than the surrounding areas. And these areas aren't empty holes, but instead they're filled with plasma. So this really, really, really hot gas. And they indicate regions of strong magnetic activity, where the magnetic fields are very, very intense. And these magnetic fields prevent hot gas from the interior of the sun from rising to the surface. So in other words, it prevents the transport of energy from the sun's interior to the surface. And that's why they appear darker and they're cooler. And sunspots are often clustered together in groups called active regions. So you can see that sometimes there's several sunspots. And in active regions, the magnetic field is even stronger and more complicated. And some sunspots can be planet-sized, and they can last from days to several months. So if you look at the image of the big sun over there, you can see various active regions. You can see various active regions, and you can see how they scale in comparison to different planets like Earth and Jupiter, which is the largest planet in our solar system. And so you can see sometimes they get up to the size of Jupiter. They can be really, really large. The images on the left were taken with DKIST, a 4-meter solar telescope on Maui. And these are actually some of the highest resolution images we have of sunspots. So these active regions, they're special because they're closely linked to these solar storms. So again, active regions are areas in the sun where there are clusters of sunspots and they have intense magnetic fields. So the image on the left shows how an idealized version of how sunspots are created. Oh, here we go. How sunspots are created by the magnetic field. And sunspots usually appear together in pairs. Usually appear together in pairs, and they have opposite polarities, so opposite charges like a magnet. And as the sun rotates, the magnetic fields above these spots end up getting twisted and tangled, and eventually tension just builds up so much that these magnetic fields explosively realign in a process we call magnetic reconnection. And this magnetic reconnection is what then causes solar storms. So again, it's similar to the rubber band analogy. If you have a rubber band and you're pulling it and twisting it and stretching it, and let's say you let go of it, it'll snap back and the rubber band will unwind. That is a similar process. And this image here, and to drive home this point. So here's a group of active regions rotating into view on the sun. So this is the visible surface of the sun, and this happened on May 29th. And so you can see these active regions, and then you can see directly in, and then the next image over here shows what the atmosphere, the upper atmosphere of the sun looks like at that region, right? So you can see all of these loops. These are magnetic field lines. You can see the sort of brightening. And this active region was actually responsible for quite a lot of solar flares. So sunspots also change number through the sun cycle, which you can see here. So the cycle lasts about 11 years, and it describes the ups and downs of solar activity driven by the sun's magnetic field. Sunspots are important indicators of the cycle because, again, they indicate when there is solar activity and when there might be more solar storms. So the cycle can be roughly divided into two parts. You have solar maximum, where you have a lot of sunspots, and then solar minimum, where you have very few sunspots. So you can think of this as a sun having seasons. And we are currently over here in cycle 25. And as you can see, we are well above solar minimum. And this is why we've seen an increase in sunspots. Now, what does this actually look like on the sun? So during solar maximum, we're at the peak of the solar cycle. This means we see more sunspots and there's more solar activity. So there's more coronal mass ejections, more solar flares. In contrast, during solar minimum, there's little to no sunspots, so there's little to no solar activity going on. So on the left, here is what the sun looks like today during solar maximum. And you can see that we have quite a lot of sunspots going on today. And over here on the right is what the sun looked like during solar minimum 4 years ago. And you can see in comparison the huge difference. But again, as a reminder, please don't look at the sun directly. I'm not liable, please don't. And I'm really happy to announce that NASA and the NOAA has officially announced that we've reached solar maximum last month, October 15th, 2024. So what does this mean? This means that we can expect more auroras, and we can expect more flares, and we can expect more coronal mass ejections in the upcoming months. So during this cycle, the number of sunspots doesn't just change. The location of the sunspots also changes. And this pattern is illustrated on what's called a butterfly diagram. And it's called a butterfly diagram because it looks like the wings of a butterfly. And so this shows how sunspots are distributed on the sun and how their locations change over time. So something I wanted to point out, so this 0 marker here, that's the equator of the sun. This top half is the northern hemisphere of the sun. This bottom half is the southern hemisphere of the sun. So we've essentially taken the sun and you sort of flatten it, and it's an average over time. So we see here that at solar maximum, sunspots appear at higher latitudes on the sun, so away from the equator. And they migrate towards the equator as we approach solar minimum. And you can see that here. As time progresses from solar maximum to solar minimum, it goes towards the equator. So at solar maximum, sometimes there's a lot of sunspots. At solar minimum, sometimes there's 0 sunspots. And again, the number of sunspots is important because they're indicators of magnetic activity on the sun. And during this cycle, the sun's magnetic field also goes through some very significant changes. So you can think of the sun as a giant bar magnet with a north and south pole. At solar minimum, the sun's magnetic field actually resembles this dipole configuration pretty closely. But at solar maximum, we have more magnetic activity, and so these fields become more twisted and tangled, which you can see here, very tangled, and we lose that clear separation between this north and south pole. So you can kind of think of this as what your hair would look like after a night of tossing and turning. It's not really going to look like this. It's more going to look like this. At least mine does. So in approximately every 11 years, what ends up happening is that the sun's magnetic field, magnetic poles flip, causing a shift from a calm sun to a more active and stormy sun. But how does the flipping of the magnetic poles happen? We're not actually completely sure, but we can observe it by tracking sunspots. So as I mentioned earlier, sunspots tend to appear together in pairs with opposite polarities. So you've seen this image on the left over here. Now translating what that would look like on the sun. So again, your equator is marked by this dashed line. This is the northern hemisphere. This is the southern hemisphere. If we focus on this pair of sunspots right here, we can see that they have opposite polarities, and I've denoted that with the plus and minus sign. The sunspot that is closer to the equator is called the leader spot, and the sunspot that's behind it is the follower spot because it follows the leader. And we can see that this polarity is actually reversed in the southern hemisphere. The leader sunspot is, in this scenario, has a positive polarity. Now, fast forward one cycle, all of a sudden we can see here that these polarities have shifted. And so now we can actually envision this with real data on something that's called a magnetic butterfly map. So this is similar to the butterfly diagram I showed you guys earlier, except this one actually illustrates how the magnetic field and how the magnetic poles change throughout the solar cycle. So this illustrates how one half of the sun's hemisphere has one polarity and how the other half has another polarity, has opposite polarity. So as the solar cycle progresses here, and again, this black line is the equator. So as the solar cycle progresses, we can see that the magnetic field migrates towards the equator, and then all of a sudden it kind of becomes zero. And when this happens, the poles flip. So you can see this here. This is the northern hemisphere, so we can see this is a negative polarity. And then in the next cycle, all of a sudden, it has a positive polarity. So what ends up happening is this reversal appears to be driven by sunspots. So the magnetic field from these active regions somehow gets transported towards the poles, eventually causing them to flip. And this equatorward flow is called the meridional circulation. However, the exact reason why this polarity happens is still a mystery. Now, okay, so we have this one flow, but what actually causes the sun's magnetic field? So our sun is a huge ball of electrically charged hot gas called plasma. It isn't a solid body. And when this charged gas moves, it generates a magnetic field. And the complex process by which this happens is called the solar dynamo. Now the sun, because it isn't a solid body, rotates differently in something we call differential rotation. The equator of the sun actually spins faster than its poles. And what happens here is as the sun, so here are the magnetic field lines. So as the sun rotates, these magnetic field lines, the plasma drags the magnetic field lines towards the equator where they become twisted and twisted over time. Now, these twists in the magnetic field can eventually come up to the surface. They become buoyant and they poke out through the surface, form what we think forms sunspots. And solar storms then are caused when these magnetic fields above these regions become even more twisted and contorted and stretched that they snap and reconnect. And this releases a large amount of energy. So again, all solar activity is driven by the sun's magnetic fields. And the more complex the fields are, the more solar activity actually occurs. But there's still a lot of open questions. So we know that magnetic fields govern most of the solar activity we can observe, but we don't really understand magnetic fields. We don't really understand well how the sun generates, replenishes, and maintains the magnetic field. And so we don't necessarily understand how the solar dynamo works. And there's still a lot of debate where the solar dynamo even begins. A very strong hypothesis is that it begins at a region called the tachocline, which is located at the base of the convective zone. So here's an interior of the sun, here's a convective zone. The tachocline would be here. And this is actually where we see the differential rotation of the sun actually happening. But recent work has pointed that it might actually happen closer to the surface of the sun. So it's still a big ongoing field of research. Moreover, we still have trouble predicting the solar cycle. It's not an easy thing to predict, and I'll discuss more of that in a little bit. Additionally, we also don't necessarily understand active regions or sunspots, their emergence. So we know they're formed when the magnetic field lines become really twisted, but we don't necessarily understand the physics behind it. This is where COFFIES comes in. So COFFIE stands for consequences of fields and flows in the interior and exterior of the sun. And COFFIES is a NASA-funded heliophysics science drive center whose aim is to create a really accurate, driven model of solar activity through a collaboration of many schools or institutions. And Stanford is a primary host institution of COFFIES. So the center's mission is to advance solar physics and help us understand what produces a solar dynamo, so that we're able to have better solar cycle predictions and we're able to predict space weather better, as well as understand the sun's impact on Earth. And now I'm going to discuss some of the science that has been going on in COFFIES. So one of the ongoing works COFFIES members are doing here at Stanford, as well as other institutions, is to try to predict the emergence of active regions. Now, and that's a really large field in itself. And these active regions don't behave nicely. They don't always form on what we call the near side of the sun, or the sun that we can see. Sometimes they form on the far side of the sun. That's part of the sun that we can't see. And so being able to image or directly image or infer active regions on the sun's far side as they come into the near side is really useful for understanding the sun's global magnetic field, as well as useful for predicting the arrival of major active regions and help our predictions of space weather. So we know that larger active regions are the ones that tend to produce more powerful solar storms and coronal mass ejections. And so we can do this using a tool called helioseismology. Helioseismology is the study of the structure and dynamics of the sun through its oscillations. So the sun is vibrating all the time. And what happens is that it generates sound waves or acoustic waves in its interior that bounce to the surface. And so we can use these sound waves or acoustic waves then to infer information from the far side of the sun and bring it to the near side of the sun. This image all the way here on the left is a near side image of the sun from NASA's Solar Dynamics Observatory. The black and white, so this is a magnetogram or what shows the sun's magnetic fields. So the black and white are opposite polarities. So these are what your active regions would look like. Right, so that's an observation that we can see. The middle image here is a far side image. So it's a predicted image using this technique in helioseismology. And these active regions here would actually be these darker areas here. Now, the very last image here shows a far side observation from NASA's stereo spacecraft. And here you can see that these lighter regions actually correspond to active regions. And as you can see here, the predicted image actually aligns pretty well with some observations from NASA's stereo. And so this is really good because we don't have a constant spacecraft that's monitoring the sun's far side. And since then, COFFIES members have also incorporated lots of machine learning techniques to be able to better predict the emergence of these active regions and space weather. Predicting solar cycles, again, I mentioned before, is also an important area of research. So knowing when the cycle will peak is also really useful for forecasting space weather. But it's still a really difficult thing to do. For instance, scientists thought that cycle 25, so our cycle, was going to be relatively weak, when actually it really isn't. So one attempt at predicting the solar cycle is to look for some observable parameters to sort of foreshadow the strength of the upcoming cycle. And so one of the most successful predictors in this case has been measuring the strength of the polar magnetic field during solar minimum. However, the caveat here is that we don't have enough data on this. But we can use models to predict what the sun will look like through its solar cycle and the next solar cycle. So the researchers here are using a model which uses the observed flows on the sun in order to simulate magnetic activity on the sun and show what the sun will look like next. So here in the image here, you can see here that this left side are observations, and with the models, they were able to simulate the rest of the solar cycle. And you can see that this shows pretty good alignment with the magnetic butterfly map I showed in previous slides. So this is really important because this will allow us to be able to predict the reversal or when the magnetic poles will switch, as well as allow us more insight into when we'll reach solar maximum. Now, the sun isn't unique in having magnetic activity or a solar cycle. Other solar type stars exhibit similar things. Other solar type stars have their own stellar cycles, which we can see here. Other stars as well can have sunspots or star spots, as they're called. But in contrast to the sun, other stars can have extremely large sunspots, actually like take up almost half of their surface, as seen here. And when I was looking through images to show this, I thought this would be really cool because here you can see the sun here, and they chose an image of the sun that in which the sun had its largest active region, had an extremely large active region to date, and you can't even see that in comparison. So other stars can have other stars are weird as well. Other stars also exhibit flares, and some even exhibit super flares, and these are tens of thousands times more powerful than the sun's. Now, looking towards the future, we can expect a lot of really interesting science to come out of this cycle. So here's an overview of some of the heliophysics missions already in operation or will be in operation. And these are only the space-based missions. I'm not even including our ground-based solar observatories. And all of these satellites, the goal is for all of them to work together so that we can better understand the Sun-Earth system. And in the interest of time, I really wanted to point out a couple missions. So we have SDO, or the Solar Dynamics Observatory, and SDO will continue to provide full disk images of the sun, providing a wealth of information about the sun's properties and its solar cycle, with the ultimate goal of helping us understand solar variations and their impacts on Earth. And SDO is actually what produced a lot of the really gorgeous images of the animations of the solar flares that I've shown. So we can expect a lot more of those really pretty images. Then we have Parker Solar Probe. So Parker Solar Probe is the first spacecraft to fly through the sun's corona, the outermost layer of the outermost atmosphere of the sun that you only see during a solar eclipse. And its goal is to study the origin and evolution of the solar wind. And something interesting that I found out was that the solar wind experiences this sort of switchback here. And so these switchbacks are reversals in the magnetic field, and they've actually been found to originate from the solar surface. So again, everything goes back to these sunspots and active regions. And something that's really interesting is that next month, Parker Solar Probe will have its closest approach to the sun. So next month we'll see this, and it'll have journeyed through billions of miles through space to just be within 4 million miles of the sun. And at its closest approach, it's gonna fly around the sun at something like 400,000 miles per hour, an insane speed. Lastly, we have Solar Orbiter. This is a joint mission between NASA and the European Space Agency. And its goal is to study the sun and observe the sun's polar regions and produce some of the closest ever images of the sun in space. And here is actually a high resolution image of the sun's southern poles that was taken in 2022. So all of these missions together will provide a wealth of information about the sun, from the solar dynamo to the solar wind. And while these are all very distinct areas of research, all of them are very important for trying to forecast space weather events, as well as understand the sun's magnetic field, understand the sun's magnetic activity and cycle, and understanding the origin of some of the most explosive storms in our solar system. And so that's all from my talk, but if at any point you have any more questions, feel free to email me at ovesa@stanford.edu. I'm always happy to answer questions. And if you're interested in keeping up with Cycle 25, NASA has a blog in which they showcase some really gorgeous images and animations that I actually borrowed for this presentation. So make sure you check out that website as well. Thank you.
Awesome. Well, that was a lot of information packed in there, Oana. And perhaps we can also bring up your last slide up. So during this session, we are going to have both questions in person and from online audience. And for the in-person questions, I will just repeat the questions so everybody can hear. Oana, do you want to sit next to me? Okay,
Yeah.
wonderful. So questions from our in-person audience. All right, right here.
Comparing coronal mass ejections with the solar flares, do they originate with the same fields happening at the same atmospheric depth, or are they different behaviors at the surface of the sun?
Great question. Okay, let me just repeat that. So when comparing solar flares and the coronal mass ejections, do they happen almost at the same depth of the same regions as you were, discussing all these features?
So that's actually still an ongoing area of research. Solar flares can come before coronal mass ejections, but they don't always occur at the same time. But from what we know, it's the twisting of the magnetic fields above these active regions that actually produces these explosive events.
Great, and there's actually another question online asking about solar flares and the coronal mass ejections. So you mentioned that these kind of like massive ejections or events, they can reach to the Earth in minutes. So is there a way for us to actually predict their arrival? Or we just go out to image and hopefully we catch something? Or are there some other advanced techniques that we can do the prediction better?
So forecasting space weather events is an extremely active area of research as well. This is a very good question. So our COFFIES team is also highly invested in trying to figure out the best way to predict these space weather events. Typically with coronal mass ejections, so I mentioned that they can reach Earth in as little as 15 hours, but sometimes it can take several days. So we have spacecrafts that are monitoring the sun that are able to see when these coronal mass ejections happen. And so we're able to forecast it that way. Another way is, as I mentioned before, because these events originate from active regions, we can track really prominent active regions. So the active regions are pretty large because we'll know that those tend to be correlated with some of these more massive and powerful storms. But at the moment, there's no foolproof technique to actually detecting these events.
Are there any kind of like machine learning techniques that might be used to, maybe helpful with the prediction? I mean, it's really relevant to our lives on Earth, just in some extreme cases.
So yeah, that's a very good question. There have been attempts to use machine learning, but again, it all boils down to the data we have in our observations. And even with machine learning techniques, we don't have a foolproof method of actually detecting when these explosive events are coming up. But a lot of researchers are actively invested in trying to make this a reality.
Yeah, well, I love how active of an area the research is. It's almost like, hey, you know, we're in this Earth-Sun system and it's so relevant, yet we do not have, you know, like fully equipped with the tools that we need. Okay, question over there.
The sun always spins in the same direction, or whatever years it suddenly flips direction? I just don't know. Sorry.
Great question. So the question was, you mentioned the rotation, especially the differential the rotation of the sun. Is the rotational direction always the same, or sometimes it also like flips directions?
That's a good question. So the sun rotates in the same way, but the equator does rotate faster than its poles.
And it is always from the west to the east?
Yes.
Okay, great. Yeah, just think about that. Yeah. So an online question. Well, okay. I love how all these questions are kind of like maybe there isn't a definite response, but Wayne was wondering what drives the solar cycle that you were talking about.
So the solar cycle is driven by the sun's magnetic field, which is driven by the solar dynamo. And again, that's a good question because I said all of this, but we're still not actually sure what actually drives the what drives the solar dynamo.
Great question.
Is there a pattern for the number of sunspots that you see at solar maximum? Are there certain cycles that are more active than others?
Great question. So if I understand correctly, you're asking whether the number of sunspots, there are still variations like during like solar, among solar cycles, or even like say during solar maximum at different points.
So good question. If you remembered one of the plots I showed with how the number of sunspots and how it changes over time, there is that sort of 11-year cycle, but the amount of sunspots in each cycle is different. And to my knowledge, we don't necessarily understand why. I mean, so the stronger the magnetic fields are and the more active the sun is, the more sunspots, but we don't actually know why some cycles produce more sunspots than others. And like I mentioned before, scientists actually thought cycle 25, our current cycle, would be very weak, but it's been proving not to be. And this question is very relevant for, again, trying to even forecast space weather and trying to predict the solar cycle, which we still don't have conclusive methods to do so.
Great. All right, over there at the back.
Yeah. What is the physics behind the differential rotation of the different flares of the sun that we showed? Like, it's hard to imagine, but when you think Earth, we can't imagine that. So why does that happen? What is the physics behind it?
Yeah, so what physics drives the differential rotation of the sun, and why? Well, hopefully our Earth doesn't rotate that way.
Yeah, to my knowledge, Earth definitely doesn't. And that is a really good question, and I'm not sure. So we know that this the differential rotation sort of begins at the base of the convective zone, where the energy starts being transported via convection. The layer below that, the radiative zone, that spins as a solid body, but it's not solid. So something is happening there that's causing this differential rotation. And that area where that happens is also where we believe the solar dynamo originates from as well.
Yeah, and there's hopefully this question is where we can get some kind of a definitive answer on. So this question coming from Jane online, asking how long does it take to arrive at the solar minimum, given now that we're in cycle 25?
So we're at the peak of cycle 25. Solar minimum started in, I want to say, December 2019. So 11 years from that.
2030 something?
Yeah,
like that?
2030, something like that. Yes, thank you.
Wow, almost yeah, hard to imagine, but we're getting there. So during solar minimum, does it actually mean there are fewer auroras and they're like less strong auroras and they're only visible in the polar areas?
That's a good question. So during solar minimum, we wouldn't necessarily expect auroras as far south as California, but again, the sun, so these highly charged particles stream out from the sun's outer atmosphere. That's called the solar wind, and that constantly bombards us no matter what. And that solar wind is present even during solar minimum. And so sometimes, you can have sort of the solar wind can become a bit more intensive, and it can interact with our atmosphere and produce auroras, but they'll mostly be located in the polar regions on Earth.
Great. Okay, question over there.
Yeah, I'm curious about something. As you know, Elon Musk is intent on putting people on the planet of Mars, but without a magnetic field, I'm just wondering, would any of these solar outbursts or solar flares be fatal to anyone, any astronaut on the surface of the moon, surface of Mars?
Oh my God, fantastic question. So the question asked, okay, with our effort now trying to put astronauts or even potentially colonizing Mars, like how does Mars, lack of magnetic field would actually like hinder us from this kind of effort?
That's a really good question. Yeah, that is definitely a problem. I mean, astronauts on the International Space Station also have to show some caution during these events because of the increased solar radiation. And definitely, I would imagine on Mars, because it doesn't have an atmosphere like Earth to protect them. So I definitely foresee potential issues there, not to mention the travel of even getting there in the first place. But yeah, that is definitely something that we have to look out for, and that's something that the Martian didn't really answer. So,
and perhaps one last question from the online audience. Brad was asking. Okay, well, I hope I don't just catch you off guard. So there's also some of you may have heard of the Carrington event in 1859. So how many times, let's say, per 1,000 years, do we estimate that kind of a storm would happen?
That's a good question. So for people that aren't aware of the Carrington event of 1859, right? So that was one of the strongest geomagnetic storms ever recorded on Earth. And so the sun released an extremely, extremely powerful solar storm that reached Earth. And what happened was that it caused auroras as far south as Cuba, and it even set telegraph stations on fire. To my knowledge, an event of that scale has not been recorded in history since then. Could it happen? I'm not sure on the probability of it happening again, but because we don't necessarily understand the solar cycle, we don't necessarily understand solar dynamo, it very well might happen. And something like that happening in today's technologically advanced world would cause a lot of problems.
Yeah, and fingers crossed it's not going to happen in our lifetimes, at least. Okay, great. Well, let's thank Oana again. So for all of you who didn't get to ask your questions, Oana will be here in person until she finishes the last question from you. So she's not going anywhere. All right, so before we end the event, I also just wanted to quickly share a few things that are coming up next. So KIPAC is now back with our regular programs. we're planning 2 stargazing events, one for the Stanford community and guests in mid-November, and also one for the general public in early December, both at the Student Observatory, which is by the golf course. So we are going to pin down the details just to make sure that we actually have a clear sky for observing, and we will be sharing more details if you follow us on social media or is on our mailing list. And also on Thursday, we're going to have an event in Spanish, Noches Astronómicas, where a few speakers will be talking about how we study galaxies, including our own, using observations, simulations, and also by building telescopes and cameras. And there will also be a panel Q&A on STEM careers and day-to-day lives of scientists and engineers. And finally, on December 5th, we're going to have another public lecture and on the mysterious fast radio bursts, which is among the brightest radio pulses in the universe, yet most of them, we have no idea where they come from. So kind of dangerous in a way. So if you want to learn more about that, that's December 5th. And if you want to keep up with what's new with KIPAC, feel free to follow us on social media or sign up for our mailing list. And we will also share all of this information shared through an email tomorrow, so you don't have to, take any notes of this. So thank you again for joining us tonight. And let's bring everybody back to the screen just to say a final goodbye. So as I mentioned, please expect an email from us tomorrow, and there will also be a very quick feedback form about this event. So we would love to hear what you like or didn't like about this event and what other topics that you might be interested in hearing about in the future so we can feature them. And this is the end of the event. So thank you very much again for joining us, and hopefully hope everyone have a great night. Thank you.